Today we're going to look at a couple of sections from chapter P, section P3 and P4. So looking at radicals and rational exponents as well as polynomials. So today we are going to be evaluating square roots. We're going to evaluate and perform operations with higher roots as well as multiply polynomials. So just a quick reminder of square roots. If b squared equals a, then b is a square root of a. So just a couple of vocabulary words to refresh our memory. That whole entire term would be a radical expression. The radical sign is going to be that symbol here, and then the radicand is the term that's underneath that radical sign. So when we're evaluating square roots, it helps to look for perfect squares when you are simplifying. So remember, perfect squares are numbers that when you multiply them by themselves. So like 2 times 2 is 4. So that's why 4 is a perfect square. 3 times 3 is 9. So 9 is a perfect square, and so on and so forth. A square root of a negative number is not a real number. So if we were to see something like that, we'd have to right now say that we have no real solution. So let's simplify. If I want to simplify the square root of 98, once again, you should be able to do these types of things without a calculator. And like my directions stated, breaking them up looking for perfect squares are probably going to be the best bet. Okay, so think about it. 98, that's an even number, so I know it's divisible by 2. If I divide that by 2, I'm going to get 49. Hopefully, we're okay with noticing that 49 is a perfect square because it's 7 times 7. So the moment I know that I have that perfect square number, think about it. Because 7 squared is under that square root, I get to take out a 7. The 2 didn't have anything that I could break down any further. It was not a perfect square, so that would have to stay underneath the radical. So this simplifies into 7 root 2. So any perfect square numbers, when you take the square root of that, square root of 49 is 7. That's why 7 moved to the outside. Numbers that are prime or can't break down any further and don't have perfect squares stay under the square root. Number 2, when we're taking the square root of negative 49, so even though 49 is a perfect square, the negative underneath the radical tells us that as of right now, we have no real solution. Okay, so anytime we have a square root, we don't know what number we get when we have a negative underneath it. So no real solution. Other kinds of roots, because square roots are not the only roots. So the definition of a principle of the nth root of a real number, so that little n that's on that square root is what is going to be called an index, and I'll show you the vocab in a second. But the nth root of a equals b means that b to the power of n equals a. Okay, so like I said, we call that it'll be a number that's attached to your square root symbol or your radical symbol. Okay, it can't be out in front. It has to be like on it, but we call that the index. So anytime that number is an even number, so 2 is the smallest even number, and that basically would be a square root. And normally when you see a square root, we don't write the index of 2, but anything like a 4 there, 6, or so on, any even number, when it says then A is having to be greater than or equal to 0, and B has to be greater than or equal to 0. Okay, so whatever the index is, if it's an even number, then that means that our answer has to be greater than or equal to 0. If our index is odd, then that means that A and B can be any real numbers. You can have negative numbers underneath underneath a radical if its index is odd. So the only time we never want a negative number underneath our radical is if the index is even. All right, so let's do some practice problems here. So if I want to simplify, this first problem is the cubed root, because that little 3 is indicating that we are cubing it, the cubed root of 72. So like last time when we were talking square roots, we were looking for perfect squares or 2 of the same number. Here, since this index is a 3, we're looking for 3 of the same number. Okay, there are a lot of different ways that you could start breaking down 72. One of the ways is 9 times 8. Obviously, those are not the same number, and I need 3 of the same number anyway. So notice that 9 gets broken down into 3 and 3. 8 can get broken down into 4 and 2. I still do not see 3 of the same number, but notice that 4 can get broken down into 2 and 2. So notice that there's 1, 2, 3 2s. And since my index is a 3, that tells us that I get to move those numbers to the outside, but I only write it one time. So a 2 is going to move to the outside. Because these 3s don't have a third 3, I'm not going to be able to break that up any further. That's going to have to stay underneath the cubed root. So 3 and 3 was really 9. So we'll keep a 9 underneath that cubed root. So 2 times the cubed root of 9 would be my simplified answer. In the next problem, that 4 is my index, so I have the fourth root of 16 over 81. Now, another way you can think of this, anytime you see division underneath a radical, you can break it up. It's really the fourth root of 16 divided by the fourth root of 81. And because my index is 4, that tells me that I need 4 of the same number. So if I start with 16, remember 16 could be 4 and 4. Those are not 4 of the same number, but notice that very easily 4 gets broken up into 2 and 2. So notice that there's 1, 2, 3, 4 2s, which tells me that because there's no other numbers left over and I have the index that I wanted of that amount of numbers, I no longer have a radical in the numerator. The fourth root of 16 is just 2. So now if I try to simplify the denominator, 81, well, that's 9 times 9. I need to have 4 of the same numbers. I can keep breaking up 9 into 3 and 3. So notice how, hey, there are 4 of the same numbers. I don't have any other numbers left over. So that tells us that 81 is going to be able to leave that radical and there won't be anything underneath the fourth root anymore. So the fourth root of 81 is 3. And now 2 over 3 doesn't simplify down any further, so 2/3 would be my simplified answer. If I'm looking at the next one, notice that my index is a 5 and it's an odd number. And so because I see a negative number underneath that radical, this time it's okay. I'm not going to say no real solution because when it's an odd index, I'm going to have a real solution. And now I need to look for 5 of the same number. Hopefully we're okay with noticing that if my number is negative underneath, I'm going to be multiplying by negative numbers because if I have to multiply a negative number by itself an odd amount of times, it's going to stay negative. So let's start breaking up 32. Once again, we're going to want to have everything at the very end be a negative number that multiplies by itself. So I'm going to ignore the negatives for a second. 32, well, that's 16 times 2, and 16 is 4 times 4, and then 4 is 2 times 2. So notice that I do have 1, 2, 3, 4, 5 of the same number. I have no other numbers left over because everything got broken down. But then, like I said, it's not that that 2 is really positive. Each of those are really going to have to be negative. A negative times a negative times a negative times a negative times a negative is going to get me that negative. And it has to be that you're multiplying by the exact same number. So -2 would be my answer. This next one, notice that we have an even index, okay? So we have to remember that rule that anytime we have an even index, our final answer has to be greater than or equal to 0. So right now I see a negative number underneath that radical, but because it's raised to an even index, an even exponent, hopefully we're okay with understanding that we're going to be multiplying that negative by itself 4 times. So I will end up having a positive number underneath the square root. Okay, so think about it. If I'm looking for 4 of the same number, so well, think about negative times a negative is a positive. So we're really dealing with 7 times 7 times 7 times 7. So really 49 and 49, and then 7, 7, 7, and 7. So really then that tells us that 7 is going to be our final answer. I would say pause the video, see if you can simplify these two problems. Hopefully these are what you got. Notice that in the first one, we could break it down to find that perfect squared number. 16 times 7. 7 is not a perfect square, so that's why it stayed under the radical. Square root of 16 was 4. In number 2, even index, we have a positive number underneath, which is good. That's what I have to have. I need to have 4 of the same number, and it turned out to be 4. Here is an application problem with radicals. So it says that the police used the formula V equals 2 times the square root of 5L to estimate the speed of a car V in miles per hour based on the length L in feet of the skid marks upon sudden braking on a dry asphalt road. If a police officer measures a car's skid marks to be 245 feet long and the posted speed limit is 50 miles per hour, was the motorist who claims he was not speeding telling the truth? Okay, so they're giving us the length of the skid marks, and that's representing our L value. We're trying to figure out the velocity or the speed of the car. So V is going to equal 2 times the square root of 5 times 245. Now, this would be the problem where I would definitely say, yes, you can use a calculator here. Okay, but in all those other problems that we did, you should be able to do things without a calculator. So if I very carefully plug this information into my calculator, we end up getting a number of 70. So that tells us because the skid marks were 245 feet long, the motorist was going 70 miles per hour. And so because the posted speed limit is 50 miles per hour, well, the motorist is lying. He was speeding. So the question says, was the motorist who claims he was not speeding telling the truth? And the answer is no. All right, so moving on to polynomials. There's 3 main types of polynomials that you guys have hopefully been familiar with in the past. Monomials are polynomials that simplify to exactly one term. Binomials are polynomials that have 2 terms, each with different exponents, so they're not like terms. And then a trinomial is a polynomial that has 3 terms. Once again, each with a different exponent. We don't want like terms. So here we're going to be practicing multiplying some binomials together. So we have x plus 5 times the quantity 4x minus 3. I like to multiply by distributing. So I like to break up this very first binomial and distribute it to the second binomial. So that means that I'm going to take the x and distribute it to the 4x minus 3. Then I'm going to go back to the original first binomial. I have a positive 5. That also has to get distributed to the 4x minus 3. So notice that I'm going to start distributing. X times 4x is going to turn into 4x squared. We add exponents when we're multiplying. X times negative 3 is negative 3x. I'm going to distribute that positive 5. 5 times 4x gives us a positive 20x. 5 times negative 3 is negative 15. We have a couple of like terms here in the middle, so to finish simplifying, we'll keep the 4x squared. Those like terms in the middle end up turning into a positive 17x. Remember, when you're combining like terms, do not add the exponents. And then we'll still have the minus 15. And notice that 2 binomials multiplied together in this case turned into a trinomial answer. In the second one, you want to make sure that you're very careful. This entire binomial is being squared. Do not just distribute that exponent to those 2 terms. You will lose part of your answer. Instead, I like to think of it as, okay, if something is being squared, you're multiplying it by itself. And then once you have it written out by multiplying them by itself, it's back to what we did in the first one. I'm going to break apart this first term and distribute it to the second. So we're going to have 6x being multiplied to the 6x minus 7. And then the negative 7 is going to have to get multiplied by the 6x minus 7. So when I start distributing, 6x and 6x is 36x squared. 6x and negative 7 is negative 42x. Distribute the negative 7. Negative 7 times 6x is another negative 42x. And then that negative 7 times negative 7 is positive 49. Couple of like terms here in the middle. Notice that if you did not multiply this out correctly, you would have lost those middle terms of x, which is then why you would not have gotten the right answer. So I keep the first term. Negative 42 and negative 42 will give us a negative 84x. And then we still have that positive 49 at the end. And here is my simplified answer. So pause the video, see if you can multiply this together. So just like that last example, we want to multiply it by itself. We have some like terms in the middle to get our answer. So that's us evaluating square roots, evaluating and performing operations with higher roots, as well as multiplying polynomials.